Hi, welcome to DCL 102. This will be part 2 in my series on basic electricity and fundamental principles of radio. Right now, the allergies in Texas are really bad. At times, if I hesitate, or you can tell my mic is muting, it's simply because I'm trying not to cough in your face or your ears. Today's topic is electricity and magnetism. These two really go hand in hand, not just in the radio world, but with electricity in general. To recap, DC current is rather simple, easy to understand. The current goes in one direction in the wire or in the circuit. Alternating current, which is what our home appliances and our entire world are powered by, is a current that reverses polarity, and the current flow reverses direction periodically. In fact, these reversals are very predictable, and their timing is actually, in all cases, really important. Now, when you get above 30,000 kilohertz, that's above 30,000 cycles per second, you enter the domain of RF, or radio frequency. In today's topic, we're going to stick with power line frequencies, which is really the world below 400 hertz. So, current flow and magnetic fields. Anywhere you have a voltage, you have an electric field. But the only way you will have a magnetic field is if there is current flowing. So the current flow in the conductor, which we usually assume to be a wire, will set up a magnetic field around that conductor. The intensity of this field, how far out from the conductor the field exists, are dependent upon the amount of current flowing. In this picture, now this is rather cartoonish, I'm trying to show you that the magnetic lines of force form a circle around the conductor. But what you're looking at is very deceptive, because there isn't just one line of force, and there aren't lines of force every so many centimeters along the wire. Think of it more as an infinite number of loops in an infinite number of places. The strongest loops are going to be very close to the wire. These loops here are spaced out from the wire, so they're relatively weak. And again, the more the current, the stronger all the fields become, but the fields close to the wire are always stronger than the fields farther from it. Now I'm going to mention something now that I'll probably never mention again, because in radio we don't care about this. But there's something called the right hand rule. If I wrap my right hand around this wire so that my thumb points in the direction of current flow, which is to the right in this picture, then my wrapped fingers around the wire show the direction of the magnetic field. Now again, in radio, we really don't care about the direction of the magnetic field because it reverses every half cycle anyway, so we really don't care, but I thought I would mention it anyway. Now, it's real important to understand a changing current flow causes a changing field. This is a concept that is vitally important because a changing or moving field will create current flow in a wire. So what we have here is we have the black wire that was always there. I've got current flowing in it. When the current starts up, this magnetic field expands out and it cuts into the gray wire. This action induces a voltage in the gray wire. Even though there's no physical contact between the two, the magnetic coupling induces a voltage in the gray wire. Now, if the current flowing in the black wire is AC, so it's varying constantly, so the field builds up and then it collapses, then it builds up in the opposite direction, then it collapses, over, that happens. That means the field is always changing, so the lines of force are always cutting into the gray wire, so there will always be a voltage on the gray wire, and it will mimic the voltage in the black wire. Now, what about DC current? If I pass DC current through the black wire, does that mean there's nothing that happens in the gray wire? Well, no, something does happen. It's just that it's not very helpful. When I turn the current on in the black wire, there will be a spike of voltage in the gray wire when the field comes into existence and expands outward and cuts through the gray wire. When I turn the current off in the black wire, the field will collapse. That will cut through the gray wire again and induce another voltage. It looks a little like this. At the top, I'm turning on a DC current in the black wire. The bottom shows the gray wire. When I turn the current on, the field expands, so there's a little spike of voltage in the gray wire. When I turn the current off, the field collapses. Since it's going the other way, the voltage in the gray wire is opposite, but it's just a very quick little spike. As you can see, DC current doesn't really work well with transformer action, because what I've just described, the interaction between the magnetic field and the two wires, is what we call transformer action. So let's talk about transformers. We know that current flow sets up a magnetic field around the conductor. We know the intensity varies depending on how much current is flowing. But what if we formed the conductor into a coil? This is going to concentrate the field that is inside the coil, in the gray area. Now, if I add some iron, which is a high permeability material, if I add iron inside the coil, the magnetic field lines become much stronger because iron has a high permeability, meaning it likes to conduct magnetic fields more than the air does. So there's those little rings of magnetic lines of force. Now, of course, they're around all of the wires. Think of an infinite number of them from one end to the other. I'm just showing you two, but there's an infinite number of them. In a situation like this, because they're all grouped together, they tend to work together, so the field lines look a lot more like this. Now, I didn't show you the lines in the middle. They loop out and go around and go to the other end of the core. I didn't show them, but they are there. They're out, spaced way out farther. They don't have a lot of influence on the circuit. They're relatively weak, but they're very strong inside the core. Very strong. Now we're getting into what we would call transformer action. If we were to take that core and extend it out and put a primary coil on one side and a secondary coil on the other side, and let's say we have 600 turns in the primary, but we only have 60 in the secondary. We've now made a voltage step-down transformer. In fact, these actually exist probably in your home right now. So let's hook it up. Let's plug the primary into power and put a load on it. If my load is 1 ohm, Ohm's law tells me I'll have 12 amps of current flowing through the load, if the transformer can handle that much current, but let's assume that it can. Ohm's law also tells me that the amperage squared times the resistance equals power. So 12 times 12 times 1 means I have 144 watts in the load, which means I have to have 144 watts coming off the outlet in the house. Well, 144 watts at 120 volts is only 1.2 amps. So you notice there's a 10-to-1 voltage ratio and a 1-to-10 current ratio going on. Now, look at the fourth bullet. There's a little loss in this system. So if I really have 144 watts in the load, the primary is probably pulling about 150 watts off the power line. Maybe not quite that much, but there's going to be a little loss. Those few watts of energy are dissipated as heat inside the transformer. So, in the primary, an electric current generated a magnetic field. In the secondary, that magnetic field generates an electric current in the secondary. Overall, transformer efficiencies nowadays are always above 95% in any design I've seen. I don't really know that I've seen one that's 99% efficient, but they are rather efficient. Now, I just showed you the schematic of a transformer, which is kind of like a cartoon view. How about we look at a real-world example of a transformer? First of all, let's look at the physical characteristics of a real transformer. You've already seen this. This is not really reality. A real transformer would probably look a little more like this. Notice the primary and secondary are wrapped around the same core. This makes those magnetic field lines really efficient. Every magnetic field line the primary generates cuts through the secondary. It is a very efficient way to build a transformer. Now, the reality is the transformer, if you take one apart, will probably look a lot like this. The windings will be inside of this odd-shaped H core, I call it. The reason for this gets very complicated, but we want to give those magnetic field lines an easy path. So we build it like this, so they stay inside the core, they're concentrated really well, and the transformer efficiency is just really good when you do it this way. So if you get a chance to take a transformer apart, you'll probably find something very close to this on the right. Now, what about all this volts and amps stuff? Let's look at the characteristics of a real transformer. Here's one I bought for a transmitter I'm building. This transmitter will be a tube type transmitter, and tubes have filaments, and filaments need current to make a lot of heat. A common filament voltage is 12.6 volts, and another common one is 6.3 volts. In this example, the primary are those two black wires soldered to those two lugs at the bottom. The secondary are the three wires at the top. There's a center tap on the secondary. You don't really have to pay attention to that white wire in that middle terminal. You can pretend it's not there. Notice the windings are wrapped around the same core in the middle, and notice the core is just like my little H-frame diagram. There's laminations all the way around, hidden under that chrome or steel frame. Like I told you, that really is how transformers are built. So if you go back and look at the nameplate on the transformer, it said it was rated for a 12.6 volt output at 30 volt amps. The math shows us that 2.38 amps would give us the 30 volt amp. Well, the catalog entry and the reason I ordered the transformer was it promised a 2.5 amp capacity. My test showed that the 2.5 amp capacity is more accurate than the 30 volt amp rating. Now, in order for me to show you exactly how all the voltage ratios work, because it's rated for 115 volts input, I decided to feed it with a variac so that I can dial the exact voltage I want. That way I can demonstrate the turns ratio and how current affects voltage exactly. So in this example, I will feed the transformer through the variac. So I dialed it right to 115 volts. You'll see I've got the voltmeter on the primary winding, right where the wires come in. I've set it for exactly 115 volts. So you'll notice there's no tubes in any of the tube sockets, so there's no load on this transformer. So when I measure my output voltage, which is specified to be 12.6 volts, I have 14.5 volts. which means my turn ratio isn't even right. It's barely even 8 to 1. Why would they design a transformer this way? Well, this is actually how transformers are designed. Because when I talked before about voltages on the secondary, I'm talking about a no-load output. Once you put a load on the transformer, because of the physics going on in the transformer, the output voltage can't stay the same. It's going to drop somewhat. If you put a very light load on it, it won't drop. But if you put any substantial load on it, it's going to drop. So let's put our tubes in. I've got all my tubes in. 2 of them I've got laying on the side because I don't have them mounted yet. I've got them wired up. And look at this. I've got a current of 2.8 amps at 12.6 volts. So you see, the nameplate was accurate. It's rated for 2.5 amps at 12.6 volts. But if you don't load the transformer enough, the voltage will be higher than that. If you load it with even more load, the voltage will keep dropping. So you might be asking yourself, well, now wait a minute. Why doesn't the voltage in my house vary when the air conditioner starts or the clothes dryer is running? Well, it does a little. It's going to drop a little. Here at the house, if I turn everything off in the house, I get 123.4 volts, about that. If I turn on the clothes dryer, the air conditioner, the oven, and the electric range and turn everything on I can drop the voltage to about 117. Now, it's only a few percent less. The reason is the transformer that feeds the house is rated like this one in volt amps, but it's a 240 volt transformer rated for 25,000 volt amps. So if I only put, if I draw 100 amps, that's only a fraction of the rating of the transformer. So for the most part, most of the time, I'm hardly loading the transformer at all. So this is something you want to think about if you're ever designing a circuit or buying a transformer, is how much stability and voltage do I need? If I need a very stable voltage, I've got to order a transformer for the right current and the right voltage. Now, of course, in most power supplies, there's regulator circuits running, and the voltage coming out of the transformer can vary all it wants to. The regulation circuits take care of it. But in a primitive tube circuit like what I'm designing here, none of that exists. So I had to order the exact right rating of transformer to get the voltage right. Otherwise, my tubes would be sitting there at 14.5 volts, drawing a little more current than they should, and they won't last very long. So one other little thing, you may or may not encounter this, but it's important that you know about it. There's a thing called the constant voltage transformer. And as you can see, the schematic diagram is a little weird. There's 2 secondaries. The big fat one down at the bottom is called a tertiary winding. And notice the capacitor across the main winding. This circuit is kind of like a tuned circuit. The secondary voltage, provided you don't exceed the current rating of the transformer, provided you are between 100% load and 0% load, the output voltage varies almost none at all. They're an expensive transformer. If the capacitor goes bad, your output voltage falls or fails completely. But in some equipment where we must have a stable voltage, they will put these in. So if the primary voltage starts to wander a bit, or if the load varies, the secondary voltage does not change. Now in some equipment, you're going to see this. This is a variation on the original. It all depends on how much load you have and who designed the transformer. But these are the only examples where load doesn't vary the voltage very much. In almost all cases, you won't have a fancy transformer like this, but I did want to mention it. Now, I said one more thing. Well, there's one more thing. If I were to have connected a 12-volt battery to that primary coil, the current would have gone very, very high. If it was a car battery, I probably could have passed 400 amps through there and burned the wire right up. But when I plug it into the wall at 120 volts, I get no mad rush of current. Why not? Well, that goes to the topic of inductance. A coil of wire has inductance, but inductance doesn't really affect DC current very much at all. But AC current it does. So another video will be coming where I talk about nothing but inductance, and I will explain how that works. As you can guess, and as you probably already know, although you may not have realized it, a tremendous amount of energy in our world is transferred with transformers. All the electrical energy you use in your home came through multiple transformers between your house and the power plant. These transformers are really efficient, amazingly so. But for frequencies above power line use, as in radio, we use RF transformers. Now, RF transformers are a completely different animal because as the frequency of the sine wave goes way up, a lot of strange things start happening in the windings and in the circuit. But again, that's a topic for a later lesson. Thank you so much for watching. I hope this was helpful. I did have to stop a few times to cough. I hope you did not hear the coughing. And in any event, I look forward to seeing you next time.